G'day guys, and welcome to our lesson on the DeBroglie wavelength. To start off this lesson, we're going to prove that even if photons don't have mass, they do have momentum. We're then going to look at the relationship between the wavelength of that photon and its momentum, and finally we're going to show that matter has momentum, we know that, and therefore it has wavelength, and that is known as the DeBroglie wavelength. So first of all, the momentum of a photon. A photon has no mass. So its momentum is given by E over C. Momentum of the photon is given by the energy in joules over C, which is 3 times 10 to the 8. And we know that energy of the photon is equal to HF or HC on lambda. So that's the energy part, and then we're dividing that by C. So this is that C down there, and this is the energy formula. And we can simplify that to H over lambda, because this C is down there, so it cancels out with that C on the top. So the momentum of a photon is H on lambda. H is the Planck's constant. And I'm going to emphasize something now, because I've made this mistake and I've seen this mistake made so many times. We know that Planck's constant can be given in joules seconds or electron volts seconds. Here is the electron volts seconds, 4.114 times 10 to the negative 15 electron volt seconds. That is not the one we use here. If you're dealing with momentum, you want to be using the Planck's constant associated with joule seconds, which is 6.63 times 10 to the negative 34. So anytime you're thinking about the DeBroglie wavelength, please make sure you're using the Planck's constant, which is associated with joules. So in this case, joule seconds. Okay. So once we've found the momentum of a photon, I think it was Einstein they brought this to. They said, yeah, we can find the momentum of a photon by taking Planck's constant and dividing by the wavelength. Therefore, we can take the wavelength and we can find that by dividing Planck's constant by the momentum. And someone came up with this. They said, yeah, it must have been DeBroglie. For matter, so we're talking matter now. Matter. We know that the momentum can be found by the mass times the velocity. So if you want to find the wavelength of matter, then you achieve that in the same way as you do for light. So you take a Planck's constant here, the Planck's constant for joule seconds, and divide it by the momentum, which is H over mv, because P for matter equals mv. It seems strange initially that there should be a wavelength for matter. The matter that we deal with in everyday life, well, that we're aware of, things like balls and cars, trains and planes, they all have very, very large momentum comparative to something like an electron. And since the momentum is large, since this bottom term is large, the overall wavelength is very low. And if the wavelength is low, they don't diffract, and there's not a lot of uncertainty in their position that we're aware of. But they've done experiments in which we use electrons and protons, things that are moving, things that have a very small mass. And if the mass is dropped there, our wavelength does increase. So thinking of the double slit experiment here, when we shine light at these slits, they then begin to act like point sources and we see them light waves diffracting out and interfering here, as waves do. We said when we perform that experiment, you've got to think of light as a wave, not a particle. Well, likewise, if we shoot electrons at these slits here, we do see the electrons diffracting out like waves. And it was G.I. Taylor's experiment. We showed that you could basically fire an electron at these slits here. And if you don't observe which of these slits the electron passes through, then it passes through them as a wave and experimentally appears to have passed through both at once because it is interfering with itself, and you get these bright and dark bands like that, just like you'd get for a photon. That shows us that matter does have a wavelength, the DeBroglie wavelength. Let's take a few everyday objects, well, one everyday object, then a few electrons, and try to calculate the DeBroglie wavelength for those examples. So I'll scale this down. Okay, we'll start out with the cricket ball. Cricket ball. Our knowns, it's got a mass of 163 grams, and we'll say it's moving at a velocity of 20 meters per second. What is the wavelength? Well, we know from this formula here, the DeBroglie wavelength is equal to h on p, which is equal to h on mv. I always like to change this kind of grams measurement into a kilograms measurement, because you want to deal with kilograms and seconds when it comes to these formulas. So 1.163 kilograms, V is still equal to 20 meters per second, so we're trying to deal in kilograms, meters and seconds. Therefore, we can work out the wavelength, 6.63 times 10 to the negative 34, all over 20 times 0.163 equals, I have here 2 times 10 to the negative 34, and that would be in meters. Wavelength is a type of distance, really, between two crests. So the wavelength of that cricket ball is incredibly tiny. And that's the reason you don't see the cricket ball diffracting or passing, through two slits at once. It behaves as you would expect it to from your experience of everyday objects. But now let's look at a very slow-moving electron. Well, an electron that's moving slowly comparative to the potential that it could be moving at. So here we have an electron. Our knowns are, the mass is 9.1 times 10 to the negative 31 kilograms. The velocity is 100 meters per second. Let's work out the wavelength. So the wavelength again is equal to h on mv. An electron is again matter. So it does have mass and it can have a velocity that varies. A photon doesn't have mass and its velocity in a vacuum is stuck at c. So we have an electron, mass 9.1 times 10 to the negative 31, v equals 100. Everything is in kilograms, meters and seconds. So lambda is 6.63 times 10 to the negative 34, using that joule seconds Planck's constant, divided by 9.1, 10 neg 31 times 100. And I have that down here as 7.29 times 10 to the negative 6 meters. This is the micrometer, 10 to the negative 6. That's 7.29 micrometers. So 10 to the negative 6 micro, 10 to the negative 9 nano, 10 to the negative 12, I think that's pico. It is possible to engineer a gap around that size. So if you were using the right technology and you did have an electron traveling at this speed, you would see a diffraction or wave-like effects happening around that gap. This gap might actually be present in things like a crystal. So if you were to fire the electron at that crystal, you would definitely see some kind of wave pattern come out on the other side, which is the basis for a lot of the results, or a basis for a lot of questions you see in the exams. So the final question we have here, it's an electron, and its energy is 2 electron volts. Let's figure out its wavelength. So I'll say here that energy in the electron is kinetic energy. So the first thing we want to do, if lambda equals h on p, which is h on mv, we know m was 9.1 times 10 to the negative 31. Let's figure out the velocity. So we take our kinetic energy and we say that's equal to a half mv squared. That's our kinetic energy formula for matter. But we have to be really careful. If I had a block of mass 1 moving at 1 meter a second, then the kinetic energy of that block is a half times 1 times 1 squared. So that's a half times 1.5 joules, not electron volts. So it would be incorrect for me to draw this. 2 equals a half 9.1 times 10 to the negative 31 v squared. That would be incorrect. I need to find that kinetic energy in terms of joules. So the way I do that is I take the 2 electron volts and multiply it by 1.6 times 10 to the negative 19. And that is equal to a half 9.1 times 10 to the negative 31 times v squared. And if I get v squared by itself here, like multiplying both sides by 2, dividing both sides by 9.1 times 10 to the negative 31, I have here v squared comes out as 7.03 times 10 to the 11. Very fast. I mean, you know, the limit velocity you can have is the speed of light. This is actually faster than the speed of light, but since it's v squared, if we take the square root of this value, we get 8.39 times 10 to the 5, and that's in meters per second. This is less than 3 times 10 to the 8. It's less than the speed of light. If you ever get a velocity for your matter that is greater than the speed of light, it is possible you've used the wrong Planck's constant, or you're still using electron volts without transforming it to joules. Because if I hadn't applied that factor, 1.6 times 10 to the negative 19, I would have got a huge value for v squared, and even the square root of that value wouldn't have brought me down to this velocity here. So if this velocity is too big, i.e. greater than 3 times 10 to the 8, check which energy values you're using. So now I've got v, we know m was equal to 9.1 times 10 to the negative 31. I can say, okay, lambda equals h on mv, 6.63 times 10 negative 34, all over 9.1 times 10 to the negative 31. times 8.39 times 10 to the 5, which is equal to, I'll calculate this, I have 8.68 times 10 to the negative 10 meters. So if this electron here, this one here, was heading towards a 1 micrometer gap, the wavelength of this electron is so small, so much smaller than that gap, you would not see any appreciable diffraction occurring. But if this gap was, say, 1 picometer, 1 picometer, then suddenly the wavelength of this electron is greater than the distance in that gap, and you would see wave effects occurring. So in summary, you find the momentum of a photon by dividing Planck's constant by its wavelength. Therefore, you find the wavelength of a photon by dividing Planck's constant by its momentum. The same formula can be used for matter. De Broglie wavelength is equal to Planck's constant over momentum, lambda equals h on p. And as long as you can figure out m and v, you can figure out lambda because h is a constant.